All right, so we're going to discuss the position function today, but before we do that, I do want to talk about what we call the AROC, the average rate of change. Okay, um, so let me put this here for you guys. Average rate of change. Now remember, the words rate of change mean derivative, right? So average derivative. And a lot of times people will say, oh, that's basically the mean value theorem. We'll talk about that later on, but it's not the same thing, okay? This is a average rate of change. And you basically see it as the change in, I guess for most of our purposes, it's going to be based on velocity. So average velocity for us is going to be the change in distance divided by the change in time. Sometimes we put delta D over delta T. Okay, the triangle, actually we should probably use S instead of D here. Delta S. The triangle means the change in. Okay, so it's the change in S over the change in T. We use S for position. Okay, so if you're trying to find the position of something, we tend to use an S function, like S of t or something like that. T is still used for time, right? But we're going to be using that as our average rate of change. Okay, now a lot of times the way you find the average rate of change, or in some cases average velocity, is just to basically use your slope formula. So you may have seen this equation written like this. So it's AROC, that's what we call it, AROC. So AROC, rate of change, is, and then we're going to say delta S over delta T, right? Which is basically like saying S sub 2 minus S sub 1 over T sub 2 minus T sub 1. So that should look familiar to just the slope formula. Okay? So other people prefer to write it a little differently. So I'm just going to show you one more. They'll use f of b minus f of a over b minus a. This one is more geared towards function. So if they gave you a function and they're telling you find the average rate of change from this point to that point, then you use the numbers they gave you, plug them in, and put them into this formula. So right now I'm going to give you an example to show you how to use this. But like I said, the most common notation that you'll see used is the very last one. Okay, the average rate of change. So let me give you an example for this. We'll keep those there. Example number 1. If a billiard ball is dropped from a height of 100 feet, so it's dropped from a height of 100 feet, its height s at a time t is given by, and they're going to give us a function. So s of t equal to negative 16t squared plus 100. How many of you guys here have taken physics? So 1, 2, 3. So some of you guys will recognize the position function, right? S of t equals to, I guess you could say, you can use acceleration, right? So at squared plus v naught t plus s naught. We're going to actually talk about that in this section. So you might actually not mind today's lesson because it might seem familiar. okay? We're going to be using a lot of the position function and the velocity functions, but I'm just going to show you how we find the velocity function from the position function eventually. But anyway, here's the equation that's given for this billiard ball, okay? Now, S is measured in feet, right? Because they said it's dropped from 100 feet, so the position is in feet, the time, I don't think I mentioned that, so let me put right here where T is in seconds. So, where T is in seconds. So what I want to do is I want to find the average velocity. Find the average velocity of the ball over the time interval (1 to 2). So find the average velocity of the ball over the time interval from 1 to 2. So from 1 second to 2 seconds. And again, if you guys had taken physics before, you should have an understanding that velocity is a vector. Okay? A vector is something that has speed and direction. So something that's traveling 65 miles an hour north, that's a vector. If something is just traveling 65 miles an hour without direction, if you're not giving direction, that's called a scalar, a constant value. But in physics, we think of velocity as a vector because you can tell whether it's moving up or down or left or right based on whether it's positive or negative, based on the circumstances of the problem. Okay, so let's find this average velocity. Again, we're going to use that equation up there, okay, A rock equals to F of B minus F of A. We're just going to use S in our equation. So let me write it for us here. So average rate of change is going to be S of B minus S of A over B minus A. So I'm just going to plug in my values, okay? So my 1 and my 2, usually we do things in alphabetical order. So 1, 2, that would be AB, right? Just like we put our points X, Y, right? X is first, Y is second. So 1 and 2, we're just going to put A is 1, B is 2. So I get S of 2 minus S of 1 over 2 minus 1. Okay, now S of 2, I'm going to have to plug that into that formula, right? So we'll just do a little scratch work here. S of 2 will be negative 16 times 2 squared plus 100. That's negative 16 times 4 plus 100, which is negative 64 plus 100. Right, so we're going to get, what is that, 36? Yeah, 36. Okay. Minus S of 1, that's negative 16 times 1 squared plus 100, which is negative 16 plus 100. That's 84. Divided by 1. Well, 36 minus 84 is negative 48. And this would be feet per second, okay? Again, how do I know? Well, because they told us that it was dropped from 100 feet high. So that means that my position is in feet. My time is in seconds, right? So this would have been in feet. This would have been in seconds, the bottom part, right? So it's feet per second. Now, it makes sense that this answer is negative. Why does it make sense that the answer is negative? Because the ball is falling, right? If I would have thrown the ball up, then the velocity would have been positive. Okay? If I would have thrown the ball to the right, the velocity would have been positive. Okay? If I throw it left, it'd be negative. So, just a real quick hint for you guys. Not that you have to know this immediately, Okay, but when it comes to directions, okay, if you go right or up, it's considered positive. So whenever you do velocity, okay, and they're talking about like, oh, someone's riding a bike from east to west and their velocity was negative 23 feet per second. Well, if they're going east to west and they say they're going negative 23 feet per second, that means they're going left, right? Because you're riding a bike left to right, right? No one rides a bike straight up into the air and down, right? So, well, at least I haven't seen that yet. Um, but an airplane flying up and down, if you see that an airplane has velocity of negative 500 feet per second, that means they're going in a downward direction. Okay, maybe not straight down, but downward direction. If they have a positive velocity, that means they're going up. Now, I think my BC class asked me or told me that their teacher had said that there is no negative velocities. And I said, that's completely wrong. There are negative velocities. I said, but there is a case where you can make it so that velocities are never negative. And you do that by mentioning the direction. So, for example, if I get on the freeway, the 10 freeway, you guys know where that is, right? Down here. And I travel to downtown LA, I'm traveling 65 miles an hour to the west, right? Or I could say I'm traveling negative 65 miles per hour, because that also is meaning going west, right? If I'm going towards Pomona, I could say I'm traveling 65 miles an hour to the east, or just 65 miles an hour, because that's positive as well. It means I'm going east, right? Direction is important when you talk about velocity, okay? You're going to see that a lot more as we do problems and things like that. You're going to notice like, whoa, wait, why is my answer negative? Oh, wait, it makes sense. Something is falling, right? Why did my velocity come out positive? Oh, they shot it out of a cannon and it's going up, right? So it's important to know what's occurring within these problems so that the answers can kind of be checked to see if they make sense. See, this answer makes sense to me because the ball was dropped, so it's going down. So its velocity makes sense that it's going down. But I could have also written 48 feet per second down. And now it's a positive answer, right, numerically, but I gave it a direction, down, right? So I guess it is right. Velocity doesn't ever have to be written as a negative number, but you better give direction if that's what you're going to do. Okay, you got to tell us which way it's going. North, south, east, west, 45 degrees. Like, give me something. So, I mean, this isn't that hard to do, right? Average rate of change. I mean, just plug in the beginning and end values and figure out what the average is. Now, you guys have done average rate of change for years, honestly. I think the first time you may have saw this is maybe freshman year, maybe before that, okay? But just that we used to call it slope. So, there you go. Now, position function. Let's talk about that. If you haven't taken physics before, don't worry. You're just at a slight advantage if you have, because of the fact that some of this stuff might make a little bit more sense to you right now, okay? Because you've seen these equations. But if you've never seen them, don't worry, it's not the end of the world. It's pretty straightforward. You're just going to have to memorize some information. And I really do mean memorize this, okay? Don't just assume you're never going to see this again. Like, this stuff does come out on AP exams every once in a while where you have to create your own position function for a problem. So you need to know where to start. So let's give you guys the information. S of t is the position you want. So do you want it at its highest point, at its lowest point, at 10 feet above the ground? Like, what do you want? Okay, so S of t is the position you want. A, this is acceleration due to gravity. Can someone give me the numerical value for acceleration due to gravity? Almost right. Nope. Nope. You said 9.8 meters per second squared. If that were true, I'd be launched off the Earth. Negative 9.8 meters per second squared.
Not bad. Not bad.
But so, someone know the feet per second squared definition? So negative 32 feet per second squared. I want to give you both because problems will be given to you in meters or in feet. Okay? If they don't mention the units, you get to choose. In which case, I really recommend the feet per second. Because notice the formula says a time half a, right? It's a lot easier to divide 32 by 2 than 9.8 by 2. I mean, I know it's 4.9, but still, right? Stay away from decimals if you can avoid it, right? So you pick whatever you want. But yeah, negative 9.8 meters per second squared. Yeah, it's very important. See, notice if you would have said 9.8 meters per second squared down, then I would have not picked on you for that one, right? But yeah, you gotta make sure you give us the direction, right? So vector is very important that we do that. Acceleration is also a vector quantity. It tells you the amount and in which direction. So let me see what else. T is time. And I guess the units just depend on what's going on, right? It can be seconds, hours, minutes, whatever. V naught, or some people call it V initial. I'm just old enough where V naught is more of a common thing. But it's initial velocity. Or V sub 0 if you want to call it that too. And then S naught, or initial position. Right? So all that stuff is important because when we read the problems, they're going to give us information. They'll tell us how fast something is moving, where it's at, that type of stuff. So you start filling in the gaps. Okay? So let's give you an example so you can see how we're going to use this stuff. So it's another one that's kind of wordy here, so just bear with me. So at time t equals 0, a diver jumps from a diving board. A diver jumps from a diving board that is 32 feet above the water. So notice they mentioned feet. So if I'm going to use acceleration due to gravity, I'm going to make sure I use negative 32 feet per second squared for A. Right? I don't want to use a negative 9.8 and mix meters with feet. Okay? Because then you got to do conversions and stuff. So I'd rather not do that. Right now I'll rewrite this equation. Okay? So don't worry. We'll get it all back up there. The position function of the diver is just kind of writing this out here. S of t equal to negative 16t squared plus 16t plus 32. Now they're giving us some information there, okay, that they're not really telling us anything obviously, but there is some information there, okay? So we'll discuss that in a bit, where t is in seconds. All right, so part A. When does the diver hit the water? That's part A. And part B, we'll do that later. It's going to say what is the velocity of the diver at impact, okay? But we'll do that after. So I know that my A value is supposed to be negative 32 feet per second squared. Now notice they already did that calculation for me in the equation because they put negative 16, right? That's half times negative 32. So they already got the negative 16 there. How fast was this diver moving initially? It's in the equation. Not zero. It's right here. Remember, that's V initial, right? So look right here. Right next to the T, that's initial velocity. Okay? So let me just kind of write this out really quick here, just for reference. You don't have to write this out. I'm just putting it up there just for reference. So notice V naught, right? V naught is 16. So that's the initial velocity of the diver. What was the diver's initial height? S naught. So 32, right? 32 feet, right? That would be, so again, just kind of highlighting this. Highlight this right here. Okay. So these are things you should be able to point out. Do I need them for this problem? I don't know yet. I'm not really doing the problem. I'm just trying to let you see some things have been given that they're not trying to be super obvious about, but it's obviously there. You just got to pay attention to the equation and interpret it, right? So when does the diver hit the water? How do I figure that out? I mean, when, what am I solving for when they say when? Time, right? So when does the diver hit the water? How do I got to figure out time. So let me write this out right here. So I want to use that equation. What do I do with it? I got to figure out t. Say it again. Yeah, set it equal to 0, because where do I want my position to be at? The ground, right? Well, the pool, not straight at the ground. You want it to be at the pool, right? That's height of 0. So I'm going to set this equal to 0. Now I'm going to divide everything by negative 16, okay? Because notice they all have the ability to do that. They are divisible by 16. So I'm going to divide by negative 16. That's going to give me 0 equals t squared minus t minus 2. Okay, and now I can actually factor, right? So here we go. T minus 2, t plus 1. So my answers for time are t minus 2 equal to 0 or t plus 1 equal to 0. So t is equal to 2 or negative 1. Can time be negative? No, right? So my only option is 2 seconds. That's how long it took the diver to hit the water. So it takes 2 seconds to hit the water. Okay, so it took 2 seconds to hit the water. I mean, that's not too difficult. And again, if you've taken physics, you probably remember doing things like this, where you're trying to figure out specific times that it took to do something, specific heights, etc. So here's the next part. B. How fast was the diver going at impact? So here's where you're going to learn a little something new. If you took physics, maybe you still remember your velocity equation. But the nice thing about calculus is you don't have to memorize equations. You can deduce them. Okay? So here's my original function. But before I write my original function, let me teach you guys something really quick. S of t is position. Okay? That's position. V of t we call velocity. We find v of t by taking the derivative of position. So if I take a derivative of position, I get velocity. A of t is acceleration. We find acceleration by taking a derivative of velocity, or two derivatives of position. So you take one derivative and then you do it again. If you have position, you take a derivative and then do it again, you'll have acceleration. Okay? Or if you're given velocity and they want you to find acceleration, just take the derivative once. Okay? They want me to figure out how fast the diver was going. They want velocity. So the only thing they gave me was a position function. So what I'm going to do is I'm going to take a derivative of that position function to find my velocity function. So let's do that. S of t is negative 16t squared plus 16t plus 32. S prime of t. What is S prime of t? So negative 16t squared, what does that become when I take a derivative of it? Someone say it nice and loud. Remember, you're just using power rule, right? You bring the power down. What do we get? Anybody? Brave soul? So I'm assuming you guys got this. Who got that? Well, why don't you say something? All right. So a lot of you guys got it. So negative 32t, right? Now, what's the derivative of 16t? Anybody? Well, what was the derivative of x? 1. So t is just a variable, correct? So what's the derivative of t? 1. So what's the derivative of 16t? 16. What's the derivative of 32? 0. Okay, there's my velocity function. So, sorry about that, but negative 32t plus 16. Now you're going to figure out, they say that the person hits the water in 2 seconds, right? So I want to figure out v of 2. Which comes out to negative 64 plus 16, which is negative 48 feet per second. That's v of 2. Now again, this answer makes sense because of the fact that it's negative. The diver did not dive up, right? When they hit the water, they weren't moving up, they were moving down, right? So, I guess Einstein might say it's all relative. But anyway, negative 48 feet per second makes sense to me. They're moving in a downward direction, and that's the speed that they were moving at, okay, the velocity. So that's it for this section. I'm going to give you guys your homework right now.